Hi, let's start with some eigenvalue problems in quantum mechanics. Okay, so we'll start with the time-dependent Schrodinger equation. That's the usual full Schrodinger equation. All right, and we'll see that in some situations there is simplifications. There are simplifications possible. One such simplification is that if the potential is time independent, okay, if the potential does not change with time, then we can have two parts. All right, we can separate the solution to two parts, one part depending on time and the other part depending only on space. Okay, we'll see that we'll get two equations, and one of them is an energy eigenvalue equation. All right, what do we mean by an eigenvalue equation? An eigenvalue equation is an equation in such a way that operator acting on a function gives you a constant multiplied by the same function. All right, it does not change the function. Okay, so we'll see that the Schrodinger equation in some situations leads to what we call as the energy eigenvalue equation. Right? So solving Schrodinger equation in these situations involves solving the eigenvalue problem. Okay, so that's what we'll look at. We'll look at some simple examples and do a couple of problems. So here is the Schrodinger equation. Here's the Schrodinger equation. This is the full time-dependent Schrodinger equation. All right, and in the case if V is independent of t, all right, if the potential is independent of time, all right, if time does not appear here, then we'll see that one part of the equation depends on time and the other part does not depend on time. All right, I mean, we can arrange things in such a way that one part depends on time and other part depends only on x, only on space. All right, this is known as separation of variables. It can be done by making this. We write psi of x comma t as psi of x multiplied by phi of t. Okay, now you might have seen these things. We won't go into much details here. We are just presenting this as some kind of a formula sheet so that we can solve problems. Okay, so if you substitute it back, we get two equations. All right, we'll say that separately they have to be equal to the same constant. We write this constant as E and we get one solution. All right, this is the first equation we get from that by separating the variables, and the solution to this is simple because this is a first order differential equation. The solution is simple. It's of the form e raised to minus I e t by h cross. All right, the second part, which depends only on space, only on x, all right, this is depending only on x. It looks like this, and we can rearrange this to look like this. All right, h cross square by 2m d square psi by dx square plus v psi is equal to e psi. Now if you look at this, you see that this is of the form of an eigenvalue equation. All right, so if you write this as h cross square by 2m d square by dx square plus v multiplied by psi is equal to e psi. Right, you see that there is some operator here which acts on psi, a wave function, in this case a function. Okay, and it gives you a constant multiplied by the same function. All right, so this is an eigenvalue equation, and we identify this operator with the Hamiltonian operator. Okay, this is known as the Hamiltonian operator. So eigenvalues of Hamiltonian operator are the measured energies, you know that. All right, so this is the eigenvalue equation we are talking about. Now the full wave function in this case, the time dependent part and the time independent part, together it looks like psi of x e raised to minus I e t by h cross. Okay, so E is the energy eigenvalue and psi is the energy eigenfunction. Okay, it's the eigenfunction of the Hamiltonian corresponding to the eigenvalue E. All right, so here psi of x is the eigenfunction of the Hamiltonian corresponding to the eigenvalue E. All right, so what we see here actually is the time dependence of an energy eigenfunction. All right, how does an energy, if the wave function is an energy eigenfunction, how does it evolve in time? The time dependence can be introduced very easily. If you know that it's an energy eigenfunction, then the time dependence can be fixed very easily. It goes like this. Okay, it's psi of x e raised to minus I e t by h cross. If this is an energy eigenfunction, then the time dependence goes like this. Okay. All right. Now the psi of x comma t is called a stationary state. Why do we call it a stationary state? Because you see that the probability, right? If you take the modulus square, we will see that it does not depend on time. Now, why doesn't it depend on time? Because the time dependence comes in this form. When you do psi star psi, okay, this term just goes away. All right, you multiply it with the complex conjugate. just disappears, right? Because E is real, energy is real, right? The eigenvalues are real, as we have said. So this just disappears, right? So this psi of x comma t modulus square is independent of time. Okay, that's why we call it as a stationary state. Okay, that's why we call it as a stationary state. Okay? Also, you have to understand that stationary states are states of definite energy. These are states of definite energy. If you make a measurement of the total energy, you will always get the same value with probability 1. Okay, so if the state of the system is represented by an energy eigenfunction, all right. This means that whenever you make the energy measurement, the answer you will get will be the corresponding energy eigenvalue. Okay, this is one of the postulates that we discussed earlier. What we will get is the energy eigenvalue. All right, and if it's in an energy eigenfunction, when you make a measurement, the state does not change. All right, when you make an energy measurement, the state does not change. Okay, so anytime you make the measurement, how many you can always get the same value of energy with the same probability, which is equal to 1. All right, so the stationary states are also called states of definite energy. Okay, this is actually true for any operator. Suppose you have some operator A, all right, and the state of the system is an eigenfunction of this operator. Let's call it as phi A. All right, it's an eigenfunction of this operator corresponding to the eigenvalue A. All right, then we can call these states phi A as states of definite value for capital A, all right, the observable represented by capital A, all right. So I'll repeat, if you have an operator, a Hermitian operator, okay, it could be momentum, it could be energy, anything, all right, any Hermitian operator, measurable, observable thing, all right. So we know that observables are represented by operators, all right. So this operator represents an observable. Right. Now, if the state of the system is an eigenfunction of this operator, all right, if the state of the system is an eigenfunction of this operator, let's say corresponding to the eigenvalue A, right. If this is the state of the system, then we can say that this is a state of definite value, or let's say definite value for the observable. Okay, observable is measurable quantity represented by operator A. All right, so operator A represents some observable, some measurable quantity. All right, then phi A corresponds to a state with a definite value for that observable quantity. All right, this follows directly from the postulates. Okay. Now, that's not the most general solution, all right. This is the full wave function, all right, but this is not the most general solution. Why? Because we know from the property of Schrodinger equation that if A and B are solutions to Schrodinger equation, then A plus B is also a solution, all right. So here we will see that there are a number of solutions. Okay, we'll label it by psi n. There is psi 1, psi 2, psi 3, etc. All right, there's a large number of solutions. So any linear combination of it, any linear superposition of it is also a possible solution of the Schrodinger equation. So in this case, the most general solution is simply this. It's summation n equal to 1 to infinity Cn psi n of x e raised to minus I e n t by h cross. All right, this together is the stationary state. Okay, we can also write it like this. Okay, now what we have done here is actually the same thing that we have done earlier. We said that we can expand any wave vector, all right, any wave vector in terms of a complete set of eigen vectors, all right. Actually we said that it can be expanded in a complete set of eigenvectors of a Hermitian operator. We had seen that the eigenvectors of a Hermitian operator forms a complete set. All right, this means that we can choose the eigenvectors of the Hermitian operator as a basis. Okay, this is what we called the principle of superposition. All right, so here what we are doing is actually we are doing the same thing. What we are doing is that we have got some arbitrary vector psi. We are expanding it using a basis. All right, and in this case, what's the basis we are using? The basis here is the eigenvectors of the Hermitian operator called Hamiltonian, of the Hermitian operator called Hamiltonian. So what we have done here is actually we are expanding a given vector. We are expanding a given vector in terms of the eigenvectors of the Hamiltonian operator. We are choosing the eigenvectors of the Hamiltonian operator as the basis set, as the basis. Okay. Now we talked abstractly about vectors in Hilbert space, etc. Here this is a representation, all right. This is a representation. Here we are representing these vectors by functions, all right. Here we are representing these vectors by functions depending on space and time, all right, complex functions. Okay. So for that reason we call this as a wave function and this as an eigen function, this as an eigen function. All right. So if you take the eigenvector and write it already in a basis called the coordinate basis, then we call it the eigen function. Okay. And again, as usual, we had said earlier that these expansion coefficients here have this interesting interpretation that the modulus square of them, right, if normalized, of course, the modulus square of them gives you the probability for making a measurement, right? It gives you the probability for making a measurement. So specifically, we'll say this modulus of Cn square is the probability for obtaining a value En on a measurement of energy. Right. So if you make a measurement of energy, if this is the state of the system, right, if this is the given state of the system, if this is the wave function of the system, then we can say that modulus Cn square is the probability of measuring a value En for energy, right. If this is the wave function representing the system, and if you measure the energy, right, if you measure the energy, what does quantum mechanics say? Quantum mechanics says that if you measure the energy for a system represented by this wave function, then you will get an energy value En with probability modulus Cn square. Again, we have also seen that after the measurement, the wave function changes to the corresponding eigen function. Right? After the measurement, the wave function changes to corresponding eigen function. This is what we called the wave function collapse, etc. So actually what we are seeing here is exactly the same thing that we had seen earlier, which we wrote as summation n Cn phi n. Okay, and we had all these postulates about measurement and eigenvalues and all that and probabilities, which we called as the generalized statistical interpretation. Okay, all right. So it's exactly the same thing. Only thing is that we are representing it in the function space. Okay, we are representing the whole thing using functions. All right, or in the coordinate basis. All right. So first we go to a free particle solution. A free particle solution, V is equal to 0. Right, it's free to go anywhere. All right, V is equal to 0. Then you write down the Schroedinger equation with V equal to 0. We get it in this form. We can write the most general solution. It's a plus e raised to ikx, a minus e raised to minus ikx. All right, and you will see that these are eigenfunctions of momentum. Okay, these are momentum eigenfunctions, also known as plane wave solutions. Momentum eigenfunctions. Okay, how do you check whether this is a momentum eigenfunction? How do you check whether this is a momentum eigenfunction? You just use the momentum operator, okay, minus IH cross d by dx. All right. So you act the momentum operator on e raised to ikx. This is a homework for you. Okay, it's an exercise for you. All right. Do this thing. You take the momentum operator. P is equal to minus IH cross d by dx. Okay, I think that's the correct momentum operator. You have to check. Okay. So you take the momentum operator and then you act it upon the state e raised to ikx, right, and see what you get. Right, you will see that you will get a constant multiplied by the same function. Okay, this is the reason why we say that this is a momentum eigenfunction. Right, you will see that in this case it's positive h cross k. So this represents a positive momentum, a momentum with the direction along the positive x-axis. So for this reason, we say that this e raised to ikx represents a right wave traveling in the positive x direction. Similarly, you will see that e raised to minus ikx represents a wave which travels along the negative x direction. All right, you can see that from the momentum. Okay, in this case it's plus h cross k, and in this case you can see that it's minus h cross k. Okay, I want you to do that. Try it. Okay. Of course, a and b are constants. Yeah. Now, if you introduce the time dependence, right, you will see that these are also eigenfunctions of energy, because energy for a free particle is given by h. Okay, you will see that the energy, these are also eigenfunctions of energy. Right. So you will see that E in this case is given by h cross square k square divided by 2m. All right. For a free particle, you will see that for a free particle, the momentum eigenfunction is also an eigenfunction for energy. All right. So if you know the momentum eigenvalue, you know the value of energy. It's p square by 2m. If p is h cross k, then E is h cross square k square divided by 2m. Right. Now, if it's an energy eigenfunction, we know how to introduce a time dependence. All right. So what I have just said, you can check this. All right. What I have just, because in this case you said the energy operator is just the momentum square, okay, divided by 2m, a constant. All right. So you see that the energy operator is actually momentum square divided by 2m. Am I right? Yeah. So for that reason, whatever function we have here, the momentum eigenfunction is also an eigenfunction of the energy operator or the Hamiltonian operator. Okay. Now, if you have an eigenfunction of the Hamiltonian operator, you know how to introduce the time dependence. All right. You just multiply it by e raised to minus I e t by h cross, where e is the corresponding energy. Okay. I hope this is clear. We have already said this. Okay. So what I have said is that if you have an energy eigenfunction, it's easy to introduce the time dependence. You just multiply it by e raised to minus I e t by h cross. Okay. All right. So that's exactly what we have done here, and here the omega is actually e by h cross. All right. It's e divided by h cross. This e divided by h cross is omega. Okay. So that's how we introduce the time dependence here. And one more thing, if it's in 3 dimensions, we can simply write it as e raised to I k dot r minus omega t. Okay, instead of kx minus omega t, it's k dot r minus omega t, and k vector will call as the wave vector. Right? And these things are important. It's important to remember that this e raised to I kx, all right, is not a normalizable wave function. You can check and you will see that it does not, it's not really a physical wave function. All right. So this means that you cannot talk about a simple momentum eigenfunction as a real thing or something. All right. What we always will have is superpositions of momentum eigenstates. We'll call it a wave packet, etc. All right. You just remember that these are non-normalizable wave functions, but still these are useful. We can always use it as a basis, etc. We can use what do you say, analogous normalization thing, and we'll call it as Dirac delta normalization, etc. We have seen these things. Okay. All right, let's not go into too many details there. We'll go into the next example, the infinite square well potential. Right? In this case, the potential is infinite. It's infinite here, and 0 inside. Okay, which means that a particle inside is trapped. It's trapped inside. Since the potential is infinite here, it cannot escape. All right. So the probability of finding this particle or this electron outside of this box, okay, this is also called particle in a box. So the probability of finding it outside is 0, because it cannot penetrate an infinite potential. Okay, it cannot penetrate an infinite potential. So it's 0. The probability of finding it is 0. Okay. So here is the specification of the potential. V of x is infinite for x less than 0. It's less than 0. Okay, it's infinite for x less than 0. It's infinite for x greater than a. All right. So these are the dimensions of the box. We have chosen our coordinate system in such a way that the 0 appears here. Okay. So that's it. And for this reason, it's known as the asymmetric potential well. All right. It's the asymmetric potential well. Asymmetric potential well. All right. Why is it asymmetric? Because we are taking from 0 to a. Right, we can also get the result for a symmetric potential, where we'll put this in the middle, and we'll say that it's minus, it's for less than minus a by 2 it's infinity, and for greater than a by 2 it's plus infinity, etc. Right, we'll come to that. Okay. So just remember that this is the asymmetric potential. All right. So the particle is confined within this region between 0 and a. All right. The particle is confined within this region, and for this reason we will see that the Schrodinger equation has this property. Whenever you have a confined system, right, whenever the energy is negative, the total energy is negative, which means that the kinetic energy plus potential energy is less than 0. Okay, this is possible if V is greater than T and also has a negative value. These are known as bound states. Okay, so you'll see that the Schrodinger equation has this property that for bound states, all right, if E is less than V, so if E is negative, let's say E is less than 0, okay, these are known as bound states. For bound states, we see that you don't have solution to the Schrodinger equation for all energy values, okay, which means that energy is discrete. For bound state, you will see that energy is discrete. All right, you will see that Schrodinger equation has solution, admits solution only for certain values of energy, not all values of energy. Okay, we also said energy is quantized, etc. Okay, so here the particle is confined within this region, so we expect that the eigenvalues, the energy is quantized in this case. Okay, all right. So that's the asymmetric infinite square well. Okay, now we can construct the Schrodinger equation, we can solve it, and the normalized energy eigenfunctions are this. Okay, it can be easily obtained. This is something that you must remember. This is something that you must keep in your mind. Okay, also the eigenvalues. Okay, you also must remember these eigenvalues. Here you see that the energy eigenvalues are discrete. Okay, it's not continuous. It can only take certain values corresponding to n equal to 1, 2, 3. Okay, one thing to remember here is that in this case we don't, in some cases we will have n equal to 0, but in this case we don't have n equal to 0. Why do we not have n equal to 0? It's easy to check. You put n equal to 0 in this wave function and you see that there is no wave function, it's 0. All right, so there is no particle, there is no solution corresponding to n equal to 0. All right, so there is no wave function or there is no particle corresponding to n equal to 0. You will see that the reason comes from uncertainty principle, because if a particle is at rest, okay, if the particle has a 0 energy inside a box, that means that you can locate it by reducing the dimensions of the box, okay, and that would violate the uncertainty relations. All these are related. All right. So in this case, you see that there is no solution for n equal to 0. You have only n equal to 1, 2, 3. All right. So n equal to 1 corresponds to what we call as the ground state. That's the lowest energy state. Okay. It's called as the ground state. It's also called as the 0 point energy. Okay. 0 point energy. 0 point energy. So remember that in order to find the 0 point energy for infinite square well potential, it corresponds to n equal to 1, not n equal to 0. Okay, that's a mistake that people commit often. Okay, after studying all these wave functions and energy eigenvalues, people forget for which cases we can have n equal to 0 and for which cases we cannot have n equal to 1. Right? So the best thing to check is that if you remember the wave function, just check whether the wave function exists for n equal to 0. Right? If the wave function is 0, that means that the particle does not exist corresponding to that state. Okay? All right. And the orthonormality relation, in this case, it's simple. As we said, A is the width of the box. All right, remember that A is the width of the box. A is the width of the box. Okay, so orthonormality relation, it can come from, you can easily check that sine m pi x by a, sine n pi x by a, integrated from 0 to a is a by 2 delta mn. Okay, which means that it's 0 if m is not equal to n, and a by 2 if m equal to n. M equal to n. Okay, so that's now this says that we can normalize this wave function, and the normalization factor turns out to be square root of 2 by a. Okay, that's exactly what we have here. All right, now this is something that you can remember. You just remember that these are normalized wave functions. Okay, these are orthonormal energy eigenfunctions. Okay, these are orthonormal energy eigenfunctions, which means that you can always have psi n star psi m dx is equal to delta nm. All right, so when you do problems involving this, if such an expression comes, you don't have to go all the way and integrate them. All right, you know immediately that it's delta nm. It's 1 if n equal to m, it's 0 if n is not equal to m. All right, so that result is already here. It's part of what you have remembered, and then you can use it directly to solve problems. All right, so in this case, this is a real wave function, so psi n star is psi n itself. Okay, psi n star is psi n itself. So this makes things a bit easier. So keep this in mind. You remember also that these are normalized energy eigenfunctions. All right, these are normalized energy eigenfunctions. Okay. Now we can also talk about the symmetric potential well. All right, we can also talk about the symmetric potential well, where we say that instead of putting it this 0 and a, what we do is that we put the 0 here. Okay, we are just using a different coordinate system which is translated slightly, and we will say that it has a width a by 2 to this side, so it's minus a by 2 to a by 2. All right, still the width is a, still the width here is a, but we have made it symmetric about the origin of our coordinate system. All right, so how do we find this thing? All right, how do we find the corresponding wave function? It's easy. We see that what we have done is we have taken x prime, we have taken a new coordinate system, and we have taken simply as x minus a by 2. All right, so we have just translated our system towards the left or towards the negative x direction by an amount a by 2. Okay, now this is our new coordinate, and we'll say that x prime, you see that x is equal to x prime plus a by 2. Okay, so if you substitute x prime is equal to, sorry, x instead of x, if you put some x prime plus a by 2, then you will get the solution for the symmetric square well potential. All right, the symmetric potential well. All right, if you just do this to a wave function, and you will get the symmetric potential. All right, and you can see that the energy spectrum remains unaffected. All right, the energy spectrum does not change, only the wave function changes. All right, the energy spectrum is unaffected. All right, another way of saying is that the Hamiltonian is invariant under translations. What we have done here is we have just translated the system a little bit, and the Hamiltonian does not know this change. All right, in other words, the Hamiltonian is symmetric under under space translations here. All right, under space translations, this is known as a space translation symmetry. How do you check whether Hamiltonian is space translation invariant? How do you check whether Hamiltonian is translation invariant? We have not talked about this, but we already know from classical mechanics that momentum is the generator for space translations. All right, so you can easily check whether Hamiltonian is symmetric under space translation by taking this commutator. Okay, if h with p is 0, then it is symmetric under space translations. We will be coming to this in more detail, I think. Now, an important thing is that for symmetric potentials, v of minus x is equal to v of x. All right, so if you have this thing here and it's 0 here, the potential here and here are the same. Okay, if you have for the potential at 1 is the same as potential at minus 1, so v of minus x is equal to v of x. Okay, in this case, it can be shown that the wave function of bound states must be either even or odd. Okay, either even or odd. This means that these are also parity eigenfunctions. All right, the wave functions, the energy eigenfunctions are also parity eigenfunctions, or we can say that the Hamiltonian will commute with the parity operator. So the energy eigenfunctions are also parity eigenfunctions, or these are even or odd. It's either even or odd. Now, as I said, we just the corresponding wave function is sin of x prime is n pi by a x prime plus a by 2. Okay, we have just made the translation x prime x is equal to x prime plus a by 2, and we get the corresponding wave function. Okay, that's fine. So it's easy to remember this. You just put x equal to x prime plus a by 2. All right, so this is x prime. Now it doesn't matter, we can call this also x. Okay, it's just a variable, we can call it also x. Okay, or we can start with the usual thing, sin of x prime is equal to, for symmetric potential well, sin of x prime is equal to square root of 2 by a sin n pi x prime by a. All right, now we'll make the translation. The new coordinate system will call x, and we'll say x, we'll say that x prime plus, x equal to x prime minus a by 2. Okay, we are translating by an amount. So this means that x prime is equal to x plus a by 2. You substitute that and you get this wave function. Okay, so it's not very difficult. You see that. Now this has a nice property. As we said, we saw that the energy eigenfunctions are either odd or even functions. Okay, it's easy to see. If you put n equal to 1, 3, 5, 7, etc., you get square root of 2 by a cos n pi a by x. You can see that from here easily. If you put, what happens if you put n equal to 1, for example? What happens if you put n equal to 1? If you put n equal to 1, you see that it becomes x plus pi by 2. Okay, what sin x plus pi by 2? It's cos, sin n pi x by n pi by a x, pi x by a plus pi by 2. Right? You know what happens with these things, and it becomes a cosine. All right. So you see that for n equal to 1, 3, 5, 7, etc., you get square root of 2 by a cos n pi by a x. All right. For n equal to 2, 4, 6, 8, etc., you get sin n pi a by x. It's not difficult, but when the problem is asked in the examination, all right, such problems can be asked. They'll just give you this range. Okay, they'll just give you this range. They'll just give you this range, and then you should know which wave function to use. All right, if it's between 0 and a or 0 and L, then you use the wave function for the asymmetric potential well. Now, if it's between minus a and a, or minus a by 2 and plus a by 2, then you have to use this one. All right, and you can this is easy to remember. For n equal to 1, 3, 5, 7, it's cosine. For n equal to 2, 4, 6, 8, it's sine. The wave function is exactly the same. All right, you remember that here the width is a. Here the width of the well is still a. Okay. All right. So these are even and these are odd functions, just as we said. All right, now we are ready to do a few problems here. Okay, these are the first 3 problems that we are going to discuss are questions that were asked in previous examinations, all right, previous NET JRF examinations. So these are previous NET questions. You'll see how these problems are asked, and these are nice problems which give you a good understanding of what's going on here. Right? So first one, the state of a particle of mass m in a one-dimensional rigid box in the interval 0 to L is given by the normalized wave function psi of x equal to square root of 2 by L. So here is the wave function. The wave function is given. All right. If its energy is measured, the possible outcomes and the average value of energy. Okay, what are the possible outcomes and what's the average value of energy? Okay, so as we said here, we see that the wave function given here. All right, so they have already given that it's normalized. Okay, they have already given that it's normalized. So let's not worry about normalization. In the exam, we cannot waste time for normalization. But I want you to check whether it's actually normalized. Right, I'll tell you how to check this thing. One way to do is that, of course, you try psi star psi in the range. Okay, but there's an easy way to do that. Okay, you just check it. You see that this wave function is a linear combination of energy eigenfunctions. We know that this is of the form sine n pi x by a. Okay, here again sine n pi x by a. Right. So you see that these are actually eigenfunctions corresponding to different values of energy. What we have here is a superposition of energy eigenstates. All right. What you remember that the normalized energy eigenstates needs this one square root of 2 by L. So let's write this thing a little bit like this. This is 3 by 5 sine. Okay, 3 by 5 square root of 2 by L sine 2 pi x by L plus 4 by 5 square root of 2 by L sine 4 pi x by L. All right, what is this actually? We know that this is the normalized energy eigenfunction. So these are the expansion coefficients C1 and C2. Okay, so you can check easily whether this is normalized by seeing if modulus C1 square plus modulus C2 square. Here there are only 2. Whether it's equal to 1. It's easy to check. You see that the square of this is 9 by 25. The square of this is 16 by 25. You add them, you get 25 by 25, which is equal to 1. So this is normalized. Okay. The only thing you have to remember is you have to use the normalized energy eigenfunctions here as the basis. That's all. Okay. So this means that what we have here is actually, let me write it as 3 by 5. You see that n. Okay, you see that this is the energy eigenfunction corresponding to, we compare it with the form sine n pi x by L. Okay, so this is the energy eigenfunction corresponding to n equal to 2. Am I right? This is the energy eigenfunction corresponding to n equal to 2. Maybe we can simply represent it by phi 2. Okay, plus this is 4 by 5. So by this 2, I am just denoting the n, because if you know the n, you know how to find the energy eigenvalue. All right, so let's not keep writing this sine thing, and this is actually, this corresponds to n equal to 4, so it's 4 by 5 phi 4. All right, what's phi 2? Phi 2 is the energy eigenfunction corresponding to n equal to 2, and phi 4 is the energy eigenfunction corresponding to n equal to 4. Okay, we don't need more details here. This is all the information that we need. Okay, so that's why I've written it in a simple manner like this. Okay, all right. Now let's look at the possible energies and their probabilities. Okay, so we know that the energy eigenvalues are given by En is equal to n square pi square h cross square divided by 2ma square. Am I right? We can just check. Okay, think, yeah, it's n square pi square h cross square divided by 2ma square. You have to remember that. Okay, so we know that the energy eigenvalues are n square pi square h cross square divided by 2ma square. So these are the possible energy values. When you make a measurement, what you get is energy eigenvalue. So if you put in this case, you see that if you know n, you can find the energy using this formula. Alright, so corresponding to phi 2, the energy is the energy corresponding to n equal to 2. So that would be 2 square. So it's 4 pi square h cross square divided by 2ma square. Alright, what's the probability for measuring a value E2? Let's say E2. Okay, you put n equal to 2. What's the probability for measuring the energy value E2? We know that it's the modulus square of the corresponding expansion coefficient. Alright, we have already said that modulus Cn square, okay, modulus Cn square is the probability for measuring an energy eigenvalue En. Okay, we have already said these things. So what we have here, wave function is written in terms of energy eigenfunctions. We have the expansion coefficients. So what's the probability for finding the system in the state phi 2 after measurement? Alright, what's the probability for, it's the same thing as saying what's the probability for measuring E2 after measurement. We see that it is modulus of this square, expansion coefficient square. So it's 9 divided by 25. Okay, so the energy corresponding, the possible energies are corresponding to n equal to 2 and n equal to 4. So corresponding to n equal to 2, it is 4 pi square h cross square divided by 2ma square, and the probability for measuring that energy is 9 by 25. Okay, all right, the other possible energy value is corresponding to n equal to 4, and it becomes 16 pi square h cross square divided by 2ma square, and the probability for measuring that is of course 16 divided by 25. All right, so these are the possible energy values and the probabilities for measuring these energies. I hope this is clear. Okay, this is easy. We just check, we just see that this, we are able to write this wave function as a superposition of energy eigenstates. Okay, fine. Now we know what happens when we make a measurement. The state will either go to phi by phi 2 or go to phi 4. After a measurement, the state changes. Okay, so the state psi either goes to phi 2 or it goes to phi 4. If it goes to phi 2, then the eigenvalue is E2. Okay, and if it goes to phi 4, then the energy is E4. Right, so I'll just write it here. What happens in the measurement is, this is the psi. If this is the psi, then if you make a measurement of energy, it either the state either changes to phi 2 or it changes to phi 4. All right, if it changes to phi 2, then we know that the energy is E2. Right, if it changes to phi 4, the energy is E4. Right, now what's the probability that it changes to phi 2? It is the expansion coefficient of this phi 2 square. Okay, modulus square. So that is the probability, the corresponding probability. Let's write it here. The corresponding probability P of E2 is equal to 9 by 16, and here P of E4 is equal to, sorry, not 9 by 16, it's 9 by 25, and it is 16 by 25. All right, I hope that's clear. Okay, this is what's happening. Now we are also asked the average value of energy. What's the average value of energy? Okay, we have already seen that the average value of energy can be found in different ways. We can find it either like this, okay, or we know that we know the possible energies, we know the probabilities. All right, so we know that the average value for energy is actually of this form: P1 E1 plus P2 E2 plus etc. Okay, in this case we have two possible results and their probabilities. So we can say this is equal to P of E2 multiplied by E2 plus P of E4 multiplied by E4. Right, this is the typical definition for average. All right, so what we mean by expectation value is the average energy. All right, these have the same meaning. Okay, you make a number of measurements, what's the average value you will get? That's exactly what we'll do here. We'll take the probability here it's 9 by 25, and the corresponding energy with probability 9 by 25, we measure 4 pi square h cross square by 2ma square. Okay, and with probability 16 by 25, we measure energy 16 pi square h cross square divided by 2ma square. Okay, so that's exactly what we'll do here, and we see that the results are in terms of h and not h cross. Okay, so in our result we have to also put h cross equal to h by 2 pi. Okay, so you look at the results, you see that it's in terms of h, so you just also substitute h cross equal to h by 2 pi, and the final result you get is 73 h square divided by 50 m a square. Okay, you can just check this. This is just what is a simple thing. Okay, check this, and we see that this is one of the options. All right, see, all right, the possible values of energies. All right, so for here also we have to put h cross to h by 2 pi. Okay, and then you will see that there's one answer with the 73 by 50 h square by ml square. So these things you can check. All right, so I think option A is the correct answer, but I want you to check this. Okay, this is how we do it. This is how we do it. So please do this problem on your own and see if you can get it right. Okay, it's a good practice problem, and it's important. All right, this was one of the questions asked. Such questions can be expected for your NET JRF examination. Okay, so I really wanted to try. I have just explained how to do this problem, so you read the question and try to do it. Okay, all right. Here is another problem also asked for a previous question. A particle in a square well. Okay, it's a square well. We see that it's antisymmetric. Fine, is prepared in a state with the wave function. It's a sine cube pi x by a. All right, the expectation value of the energy of the particle. We are asked the average value of the energy of the particle. All right, now how do we do this? Okay. Now one way to do that is the brute force method. We can just do psi integral psi star of x h cap psi of x, something like that, and then do the integration, and you see that it's sine cube, so when you do these things it may get a bit complicated. Okay, but there's another trick. We see if we can write this wave function. You see clearly that this is not an energy eigenfunction. Okay, this does not have the form of an energy eigenfunction for a square well potential. All right, so can we expand it, okay, in basis formed by energy eigenfunctions? Okay, so the thing is, can we write this function, the sine cube pi x by a, can we write it as a superposition of energy eigenstates? All right, so this cube is a bit worrying here. We know that in our energy eigenfunctions we don't have any cube. Okay, so we use this relation. We know this relation sine 3x. Okay, sine 3x is equal to 3 sine x minus 4 sine cube x. Am I right? Yeah, sine 3x is 3 sine x minus 4 sine cube x. There's a relation like that. You can check. All right. So from here you see that sine cube x can be written as sine 3x minus 3 sine x. Sorry, plus. Yeah, it's correct. Sorry, 3 sine x minus sine 3x divided by 4. Okay, that's exactly what we have done here. Okay, this divided by 4 I have taken outside, so it's 3 sine x minus sine 3x. 3 sine x minus sine 3x. It's correct, right? So it's 3 sine x minus sine 3x. Okay, so we have made use of this trigonometric identity. Please check this. Okay, I'm just writing it down from my memory. So please check this. You know that there is a relation of this sort. You have to check. Don't take me at face value. Just check if this is correct. And using that, we can write this in this form. Okay, here the wave function is not normalized, so there's this a by 4. Now a by 4, a is a constant and a by 4 is another constant, so we'll simply write it as a again. Okay, we'll simply write it as a again. All right, it's 3 sine pi x by a minus sine 3 pi x by a. All right, we see that this is not normalized. Okay, these are energy eigenfunctions. We know this is of the form sine n pi x by a. Okay, these are not orthonormal, so we'll have also we can also multiply and divide by square root of 2 by a here, square root of 2 by a here, and then you have to multiply and divide, so outside there will be a square root of a by 2. Am I right? Okay. I hope this is clear, right? We can multiply by a square root of 2 by a here and a square root of 2 by a here, okay, which means that outside there should be a square root of a by 2. Okay. Now, since all these things are constant, again we will redefine our constant as a by 4 square root of a by 2. We'll simply write it as a again. Okay. It's some other constant. We have to fix the constant anyway. Okay. Now we can write this as, this is corresponding to n equal to 1. So this is 351 minus 53. This is n equal to 3. Okay. By this number I am denoting n. So this simply can be written as a multiplied by 351 minus 53. Okay. Now we need to find this a. We need to find a. Okay. So what's a normalized wave function? This is the wave function. Find what's a normalized wave function. Normalized wave function is, we have expanded the wave function in terms of a basis. Okay. So we know that the total probability should add up to 1, which means that we have already seen summation I modulus c I square has to be equal to 1. We can use this to normalize this a. Right. Now you could also normalize by saying that psi star psi is equal to 1. Sorry, psi star psi dx is equal to 1, but you will see it's very complicated. Okay. This is easy. We are working on a discrete basis, so we can write it as c1 square is 9a square and c2 square is a square. So 9a square plus a square is equal to 1. So a square is 1 by 10 and a is 1 by square root of 10. So you substitute it here, you get the normalized wave function. Okay. It is 3 by square root of 10, phi 1 minus 1 by square root of 10, phi 3. Alright. Now again we know that the outcomes of energy values are E1 and E3, possible outcomes, and their probabilities are 9 by 10 and 1 by 10. Right. It's exactly as we saw before. So the average value is again P1 E1 plus P3 E3. This is the definition for the average energy. All right. If P1 is the probability for measuring energy value E1 and P3 is the probability for measuring energy value E3, then the average value is simply P1 E1 plus P3 E3. We know how to find all of these things. All right. We know P1 is 9 by 10 and we know P3 is 1 by 10. Okay. The generalized statistical interpretation. What's E1 and E2? E1. We know we'll use En is equal to n square pi square h cross square divided by 2ma square. So E1 is simply pi square h cross square by 2ma square E1, and E3 is 9 pi square h cross square divided by 2ma square. So you just use it here to find the average value. All right. So it's 9 by 10 modulus the probability 9 by 10 multiplied by pi square h cross square divided by 2ma square, the energy value, and then this is the probability and multiplied by the energy value 9 pi square h cross square divided by 2ma square. Okay. And you will see that the final result is 9 pi square h cross square divided by 10 ma square. I want you to check this, of course. All right. This is what I got in my calculation, but you have to check. This is the way to do that. Okay. This is the way to do it. I want you to check this. Okay. I want you to do it by yourself. Okay. Now, if you did not remember the sine cube thing, you see that the things can get very complicated. All right. Of course, we can do it without remembering this thing. Right. Of course, we can solve this problem without remembering it. You just use the usual definitions and you do psi star of x h cap psi of x dx within the limit 0 to a, and you will get the average value of energy. Okay. But you see that our method is much easier. What we did is that we saw that there is a way to write this. We are asked to find the energy. Okay. So we see that there is a simple way to write this wave function as a superposition of energy eigenfunctions. Once we do that, the rest is straightforward. All right. That's what we have done here. Okay. Now here is the third problem. Here is the third problem that we will do today. Actually, I will leave it as an exercise. Okay, this is an exercise. I want you to do it. Okay, this also was asked for a previous question. I will explain to you how to do that, and then you can do it. Okay, a particle is in the ground state of an infinite square well potential given by V of x equal to 0 for minus a less than or equal to x less than or equal to a. Okay. Okay, the probability to find the particle, it's infinity otherwise. The probability to find the particle in the interval between minus a by 2 and a by 2. is. What's the probability of finding the particle between this? Right? We know that the probability of finding the particle in a position can be found by integral. That probability density is given by psi of x, modulus of psi of x square. Okay, so if it's within a region, you just do minus a by t to a by 2 psi of x square dx. Okay, because we have to find the probability to find it within the region, minus a by t to a by 2. So this is the answer. This is the answer. All right. The only subtle issue here is that we have to write down psi of x. Okay, so that's given. It's in the ground state of an infinite square well potential. Okay, it's a ground state. It's the ground state, which means that it's n equal to 1. Okay, we see that it's a symmetric potential, so we know that we have to choose square root of 2 by a cos n pi x by a as the wave function, because n equal to 1. Okay, so the ground state wave function is, so I have put n equal to 1. This I have taken directly from here. Okay, I've taken it directly from here, square root of 2 by a cos n pi x by a for n equal to 1, 3, 5, 7. Okay, so it's given that it's on the ground state, so we do, what we do is, we just put n equal to 1. Okay, so we know the wave function is square root of 2 by a cos Okay, we know the wave function for n equal to 1. The ground state wave function is psi of x equal to square root of 2 by a and cos n pi x by a. Okay, here n is 1. So the ground state wave function is this. So we have the wave function, all right? But you have to be very careful. You remember that this a was the width of the square well. Okay, the a was the width of the square well, right? So instead of here, actually what you need is the width of the square well. Okay, in this case, what's the width of the square well? It's minus a to a. It is minus a to a, right? So minus a to 0 is a and 0 to a is a. So the total width here is 2a. Okay, we did this thing for minus a by 2 to a by 2, and then this is fine. And you remember that this a was the width, all right? In this case, it's minus a to a, so the width is twice a. The width is 2a. So that means that you have to put a 2a here and a 2a here. All right. Remember, what should appear here is the width of the potential well. All right. It's the width of the potential well. So you don't just write square root of 2 by a. It's square root of 2 divided by width of the potential well. Okay. Square root of 2 divided by width of the potential well. Maybe we can write it as L. Then it's more clear. Okay. L. And what's L? L is the width of the potential well, and in this case it is 2a. In this case it is 2a. Right? So this is actually square root of 1 by a cos pi x divided by 2a. This is your wave function. This is your wave function. Okay. Now once you have the wave function, this is given, this we find from what's given in the question. Once we find the wave function, it's an easy thing. It's child's play to find the probability. What you do is that minus a by 2, minus, we are asked to find the probability minus a by 2 to a by 2, okay, between the region minus a by 2 and a by 2. So it's minus a by 2 to a by 2, psi star psi dx. Okay, in this case psi star psi is 1 by a cos square pi x by a dx. You just have to integrate this and you will get the answer. Okay, the answer what I got is option B, but you can check, and if my option is wrong, you can explain it to me why it is wrong, etc. But this is how we have to do it. Okay, I want you to do it, and it's a good problem. All right, now how do you integrate such integrals? How do we do such integrals? If you have integral cos square x dx, what do? You write this cos square x as, we know that cos 2x, there is a relation cos 2x equal to 2 cos square x minus 1. So we can write cos square x as cos 2x plus 1 divided by 2. Okay, that's exactly what we'll do here. We'll write cos 2 pi x by a, 2a here. Okay, remember it's 2a. cos pi x by 2a here. So you just do this, it's cos 2x, so it will be cos, that 2 and 2 will get cancelled, so it's cos pi x by a plus 1 integral dx. Now you know how to integrate these things, alright. If it's cos x, the integral is just sin x. If it's cos ax or cos lx, it's sin x divided by l, etc. Okay, so you can do that. Do this, apply the limits a by 2 and minus a by 2, and you will get the answer to be 1 by 2 plus 1 by pi. Okay, now I think we'll wind up the class for now. Now you have to try this, and you please contact me if there's any difficulty in doing the exercises that I give you in the class. Okay. Now I suggest that you study the problems then and there. All right, you work out the problems then and there. You can pause the class and then work out the problems in between, or you can actually start doing the problem before I explain to you the result. All right, before I explain to you the steps. Okay, and that will get you familiarized with these kinds of problems. Okay, it's just a matter of a little bit practice, and then you will find these problems quite easy to do. Right? Only thing is that there are some kind of simple integrations that you have to do. For example, here integral of cos square x dx. That's quite simple. Okay, it's cos 2x plus 1 by 2 into integrate. Integration of cos 2x, we know that it's sin 2x by 2, and integral of dx is just x, so it's just a matter of applying the limits correctly. Okay, this is a simple integration. Please do it.